All right. So let's double check that math. We've got 3/4, come on, 4th, 5/12 plus 3/6, which is just 1/2, plus 3/4 and 1/2 is 9/8. Yeah, okay. Yep, we right. Cube root of 603 over 6, because then we're on a cube root. And I have a cube root of 24 breaks into 2 cubed by 3. So I need another pair of 3's to get out of radical jail. Okay, so, hi? Yes, no? Oh. So I'll have 3 2's and 3 3's. Cube root of that is a 2 times a 3 is a 6. 67 by 9 is 603. Which is the nth root. I don't have the nth root. Let's do this. Cube root of that. It's the effective amount of sleep that I got. Baby bear sick. I was up on the couch with him all night because the only way that he could pass out is if he was upright. So, be kind today, because I haven't had a night this bad since he was an infant. Let's math!
Oh boy.
This is going to be a train wreck. All right. Again, if you did not grab your notebook, I did not get to them. I honestly thought no one ever comes in during Spartan time. I thought that I'd be able to get stuff in. There were a couple of freshmen who came in to do review, and then we were working clear after school. So I never got to the notebooks. If you need it, take it. Otherwise, if you do not need your notebook for later in today until the end of the day, you are welcome to leave them here again, and I will go through them during third hour. I'll just pump myself full of caffeine until I can see straight. Okay? So, we're going to hop straight in. 4.1 is all about review of right triangle trig. You saw all of this in geometry. If you don't remember geometry, which last year was... Okay, the last 2 years have been difficult to describe without the word cluster. And somewhere in there you have done geometry. Last semester, I had a bunch of kids in PreCalc who had geometry during the shutdown, so they literally didn't do half of the course. Okay, so I know that for a chunk of you, not only has it been a long time, but it's also never been seen. You're just going to have to keep up. You're going to have to do something extra to get this under wraps, okay? Right triangle trig, there's an entire unit on it in geometry. It is all based on, we started to talk about it the other day until the middle school like hit a sign or burnt down the gym or something. I don't know what that was. In a right triangle, you have your 3 defined sides, opposite, adjacent, hypotenuse. We talked about your angle. If you have not ever seen that notation before, that little feller is called theta. What we need to be careful about is empty set is not the same thing as theta. Okay? Theta is Greek letter, and we use it for the angle. Specifically, an amount of rotation. Okay, we're going to start talking about rotation about a circle in this chapter. And this, I said, this is the big kahuna. This is the like 3-week-long unit that gets you ready for trig. You're going to review a good amount of this stuff in the first part of trig, but y'all got to know this if you want on to the next class. Okay, that's why we take so much time on it. When we say theta is rotation, not necessarily just an angle, that's because you're used to coordinates in terms of horizontal and vertical movement, x, y. What you're going to start getting is polar coordinates instead, where every coordinate is your radius and the amount of rotation. So think about that. If everything starts at a certain position and I rotate this far and I stretch out this far, radius, it's still a location, right? So we're laying the foundation for that. But we got to remember the basics first. Opposite, adjacent, hypotenuse, and then SOHCAHTOA. Okay, that's the basis of right triangle trig, that and Pythagorean theorem. That you should have had from back in the day. You got to put a little phlegm on it when you pronounce them. SOHCAHTOA. So you can get those H's in there. What it means is sine of an angle is opposite over hypotenuse. The cosine of an angle is adjacent over hypotenuse. The tangent of an angle is opposite over adjacent. And when you move on to trig, this is how you start to create a bunch of trig identities. Remember how you had a bunch of theorems and postulates and axioms and stuff in geometry? Well, the way that you first start to prove those and then use them later, you're going to use these 3 basic definitions to create whole identities within trig. These are the ones you were introduced to in geometry. The ones you may not have seen are their backwards redneck cousins. The reciprocal of sine is called secant. I take that back, it's cosecant. I said I'm tired. Cosecant of an angle is hypotenuse over opposite. Secant of an angle is hypotenuse over adjacent. And the cotangent of an angle is adjacent over opposite. These are my 6 defined trig ratios. What's up?
On our calculator, it says sine to the negative 1. Is that just the same?
No. Remember, and that's something that bothers me. Remember that if I say x to the negative first, that means 1 over x to the first. But as soon as I apply a negative 1 to the name of a function, it has a different meaning. Now it means inverse. Well, if I'm saying the sine of x, and then I put a negative 1 on the sine, on the function itself, has a different, those are arc functions. And we're going to get to those in a minute. These don't exist on your calculator. You just got to know them. Also, you can just do the reciprocal button of this. Maybe it would be nice to put next to these that in terms of a calculator, say I'm trying to graph this. We're going to learn how to graph all of these, and no, you cannot just do it in a calculator because the calculator ain't going to do it in terms of pi, and we have to do it in terms of pi because calculators will only give you decimals. I could do this as 1 over sine of theta. I could do this as 1 over cosine of theta. I could do this as 1 over tangent of theta. And that's actually how you do them in the calculator. Okay? Whew. So, they're trig ratios. A ratio is just a comparison. I'm comparing these two sides on a triangle. That's all I'm doing. For example, any other ratio, think of another ratio that's commonly used. Dollars per hour, miles per gallon, prom's coming up. How many guys and girls are on the dance floor? Okay, there's a ratio, right? A comparison. That's all these are. I'm going to compare those side lengths. I don't remember where we got before we were interrupted, but how do I know who goes where? Okay, opposite is literally across opposite from the angle you're talking about. Remember the gator mouth? Okay, opposite is the stick you jam in the gator's mouth so that you don't get bit, or the bone you throw in the rancor's mouth so Luke doesn't die. Okay, hypotenuse, always across from the right angle. It's always going to be the biggest angle. There's a triangle proportionality theorem from geometry that says the biggest angle is always across from the biggest side. Smallest angle is always across from the smallest side. Okay, think about like if you have siblings and like difference in ages. Like you're in high school, the next one's in middle school, the next one's in elementary school. Y'all gonna get the same slices of pizza? Okay, you have the metabolism somewhere between a black hole and a trash compactor. Okay, enjoy it. It goes away. Whereas the middle school kid, maybe not so much. The elementary kid, maybe like one slice, and then they pick off the pepperoni. Okay. The biggest angle gets the biggest side. The biggest kid gets the bigger chunk of pizza. Okay. So I always know hypotenuse has to be the biggest. Opposite and adjacent can change as long as it's a right angle. Right? It still has opposite, adjacent, hypotenuse. Hypotenuse is still the biggest one. So with that, we have to be able to define what those ratios are. And we always have to reduce them. Okay, before I go on, please tell me you know Pythagorean theorem. It's like a 6th grade standard. Right above Matt's head, not only the Pythagorean theorem, but the 5 axioms of Pythagoras' cult. If you didn't know that, if no one told you that in geometry, Pythagoras was actually a cult leader. He believed that he and his followers believed that since everything was physically measurable, everything was describable by geometry, so I could describe the entire universe with math. Therefore, if I know enough math, I become omnipotent. If I'm omnipotent, I become immortal. They genuinely believed that if you learned enough math, if you explored enough mathematical concept, you could become a god. The Greeks, right? Like, hey, it needs to rain. You know, Persephone, you gonna help me out? Okay. Yeah. It's more like they would sacrifice one of you. Like, who here has? Nope. Nope. Not going there. Whew! That was close. If I'm going to put in my trig ratios, first I identify, here's the angle that I'm going from. I'm going to say this is my opposite, my adjacent, my hypotenuse. And then I state the sine of theta is, the cosine of theta is, the tangent of theta is, the cosecant of theta is. The reason that it's cosecant, reciprocal of sine, is because if it was cosecant was the reciprocal of cosine, that's kind of like cosine, and just sounds weird. So secant of theta and cotangent of theta. Now in this case, these are all relatively prime numbers, meaning when I set up my ratios, nothing's going to reduce. Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Cosecant, hypotenuse over opposite, just flip your sign. Secant, hypotenuse over adjacent, just flip your cosine. 15. And cotangent is adjacent over opposite. Flip your tangent. Okay? And you always need to make sure that you simplify these wherever possible, you reduce these wherever possible. And what happens if, rut-row, Raggy, what if that was 8 over square root of 17? You better rationalize that, okay? Anyone remember talking about Pythagorean triples?
5, 12, 13, 4, 5. 3, 4, 5.
Okay, the three most common Pythagorean triples. Pythagorean triples are integer sets of numbers that will satisfy Pythagorean theorem. So I don't have to use radicals anymore. 3, 4, 5, the most common. And they really like to use these and then scale them up or down because they're not original to make other triangles. So like instead of 3, 4, 5, maybe I called it 55, 44, 33. Right? It's still a 3, 4, 5 triangle, it's just 11 times as big because it maintains the ratio. 3, 4, 5, 5, 12, 13, and 8, 15, 17 are the three first Pythagorean triples. You're going to see them a lot in the right triangle trig sections. So this is more just practice. Identify what the angle is, label opposite adjacent hypotenuse from that angle, and then tell me all the stuff. Homework hack if you ever have to do more than one of these. Set it up like a table. That way you don't have to keep rewriting those. Now I'll probably make sure that you only have one of these, but Well, you might remember from geometry about these, as soon as they start twisting, turning, rotating that triangle to an orientation where it's not nice and neat, where, you know, theta is down here and your base is perpendicular, and like, if they're going to start turning it like that, well, turn the paper until it looks the way you want it to. Okay? My oldest just figured out that trick for coloring in the lines. If I just turn the paper a little bit, then it's easier to color in the lines. He feels like a genius. Like, figured it out, bud. Why did I only put those three? Because then I just flip them. I just know which one is which. The cosecant is reciprocal of sine. The secant is reciprocal of cosine. And the cotangent is reciprocal of tangent. Same thing here. 13 fifths, 13 twelfths, 12 fifths. Double check that none of them can be reduced. Let's look at the top half and see if we can come up with some assumptions or conclusions. What's something that you could say about sine and cosine? Because they're both over the hypotenuse, they're both going to have the same denominator. What about the values themselves? What do you notice about every one of the sine and cosine values? I thought I heard it. They're all less than 1. They're all proper fractions. Which is true because if I'm comparing something to the hypotenuse, and the hypotenuse is always the biggest side, doesn't that mean they're always going to be something over biggest? So they're always going to be less than 1. Or later, as we start getting into negative angles, between -1 and 1. If you ever try to do the sine or cosine and get a value outside of 1, that's illegal.
Is that like a commandment of domain?
Dun 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 dun. It's coming. Okay. I can also use one that I already have to find the rest of them. If I know that cosine is this, go find the rest of them. So I will start by drawing arbitrary right triangle. It doesn't matter if it's to scale. It just needs to be a right triangle, because we're going to label it accordingly. We'll throw theta somewhere in a corner that is convenient for us. You don't even have to do this. It's just when we're first seeing these, it's handy to have it drawn in front of us. Maybe you remember the old geometry axiom, when in doubt, draw it out. Okay? So if the cosine is 2/5, what do I know? Adjacent and hypotenuse. So the adjacent is 2, the hypotenuse is 5. What I don't know is the opposite, but here comes our good old friend, the cult leader. Okay. What are A, B, and C? Okay. Leg, hypotenuse. The way that when I taught geometry, it's been like 10 years, but the way that I taught geometry is I told kids, if you want the shortcuts for these, well, if I'm looking for the hypotenuse, aren't I going to put number, and then square root it? So I'd have them write just the little shortcut of the hypotenuse is square root of leg squared plus leg squared. Doesn't even matter what's A or B. If I'm looking for a leg, on the other hand, say I'm looking for A. Well, I'd have this number, I'd subtract that number, and then I'd square root. So the leg is the square root of Hypotenuse squared minus leg squared. If those little cheater shortcuts help you, use them. I'm going to default to stuff like that because, again, we're assuming in PreCalc that you did all this in geometry. I know that that's not true. I'm going to say you're going to get really tired of the words in geometry in this chapter. So if there's ever something that I just do or say and you're like, whoa, 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 what? Where the crap did that come from? Stop me, okay? So I'm just going to write this out as 5 squared minus 2 squared. Like, that's what I'm getting at, is it's assumed that you know how to do all this because you passed middle school. Okay, so 25 minus 4 is 21, so it's the square root of 21. Now go find all the rest of your stuff. The sign, maybe I should label those again. Opposite, adjacent, hypotenuse. Sine of theta, opposite over hypotenuse, square root of 21 over 5. Cosine of theta, they already gave me, 2/5. The tangent of theta, opposite over adjacent, square root of 21 over 2. And then all of their compatriots, their reciprocals. The cosecant of theta, I flip this and I rationalize. I know you can rationalize these if you have to write it out. If you can do it on the fly, you should be able to. Maybe it just takes a little practice. You're going to have to multiply by square root of 21 and square root of 21, right? So I get 5 root of 21 over 21. If you need to write that out, write it out. Write 5 over square root of 21 times square root of 21 times square root of 21, and then go on down the road. Now, the reason I know you can do that, every day when I come into the building, I walk past Mr. Jameson's room, who literally has this on the board for Algebra 1. They are doing this right now. Rationalizing, doing things like binomials, 3 square root of 5 plus 2 square root of 6 times 2 square root of 5 minus 1 square root of 6. They're doing that right now in Algebra 1. Okay, so I'm just going to kind of fly through these instead. The secant of theta, 5/2, and the cotangent of theta is 2 root of 21 over 21. Okay, so you got to flip them. Rationalize them. Simplify them wherever possible. What happens if, what if this ended up as square root of 21 over 3 and then I flipped it? Remember, right now I can't do anything with these because one's in radical jail and one is not. As soon as I flip that and rationalize, I get 3 root of 21 over 21. Now these are both out of radical land, so I can reduce it. Okay? So it's expected that everything we're doing going forward, because you've done it all before, you can write it in simplified radicals, pi, I, e, fractions, the whole works. So, I give you tangent. Actually, before the meds happened, there was a lot of tangents. I give you tangent, you get the rest. Draw your arbitrary triangle, put things in spots, Pythagorean for the missing part, game on. And a reminder that all of this stuff, top right corner over there. Pythagorean theorem, and all 6 of our trig ratios, right up there in the top corner. Found all those cute little posters hiding in the closet of the guy who had PreCalc before me. He refused to put them up because he thought that any form of notes on a test was cheating. Make sure you put stuff in the right spot. Make sure you Pythagorean correctly. Okay, double check your rationalizing. Notice that every one of these is going to be written in terms of simplified fractions or radicals. Okay, for those of you who did Algebra 2 last semester, okay, if you had me, I know that I always get grumbly in Algebra 2 when kids don't know how to write things in fractions and radicals. Because you should have been doing it from the second that you learned it. All throughout geometry, you should have been working in simplified radicals. And I know that they just kind of let you do decimals and not think. Okay. All the stuff that we did with calculators, you should have done it in Algebra 2. If you never ran an 84 before you got in here. Okay, and that's why I get kind of grumbly about things, is it's all stuff that you should have done before. Are we doing okay with it? Write things in the right spots. If you have to write out times square root of 5 over times square root of 5 and then simplify the expression, write it out. You use what you need to. Okay, I'm the math teacher. Sometimes I'm busting out fingers and I'm counting on fingers. Okay, you use what you have to. All right. The 30, 60, 90, 45, 45, 90. This page right here. I've told you before that I firmly believe you should have access to notes for everything. That is a core philosophy of how I believe education should work. Real functional adults look things up. This chapter, you're going to get one of the few times where I take that away. These and the unit circle, which is just this on repeat mode, are so critical to moving on to trigonometry that several times throughout the chapter, I'm just going to toss this up and say, put everything away, scratch paper, fill it out. You have to know these. because you should have been doing these since I think the first time you saw them was middle school. You should have beat the crap out of them in geometry. They're that important. So if you need to flashcard, Quizlet, Kahoot, I don't care, do something, you got to know them. Because we will take, at some point in this chapter, one quiz. No notes, no nothing. Everything gets put away. No calculator, no diddly, nothing. Here's a piece of paper, fill it out. And it's all based on these things. So lock it in. These are important. Start with the 45, 45, 90. The genesis of it is a square. What happens? Okay, what do you know about a square? Okay, I heard all 90s. I heard all the sides are the same. Come on, well, we remember about our quadrilateral unit. Diagonals are congruent. Diagonals are perpendicular bisectors. Diagonals are also angle bisectors. The sides are parallel, so it's also a parallelogram. All this different stuff, it's perfect. What happens when I cut it in half? Those two legs are still congruent. And because those were angle bisectors, those two angles that used to be 90 are now what? That's where this comes from. So that's also how I'm going to derive my information for it. If I know that this is, let's say, x. I don't know what it is, so I'm going to put a variable. Then this is also x. Can you find the hypotenuse? Use Pythagorean theorem, find the hypotenuse. X squared plus x squared square root, right? Well, that's 2x squared. Simplify it, x root of 2. So regardless of what x is, it's going to have that ratio of 1, 1, square root of 2 times x, whatever the force multiplier is. So next to this, you should write those special ratios 1, 1, square root of 2. You may have seen this before as literally ratio 1, 1, square root of 2. And then I expand that by throwing variables in there, x's. Okay, so if I know that, womp, then come over to your table here, and under 45 degrees, if you know theta is 45, 1, 1, square root of 2, fill her in. What's the sign? Opposite over hypotenuse. Square root of 2 over 2, because you have to rationalize. Now, thankfully, square root of 2 over 2 is also the cosine because the legs are the same. Tangent. Opposite over adjacent. 1. Cosecant. So now instead of opposite over hypotenuse, it's hypotenuse over opposite. No negatives, just square root of 2. The negatives come later. Just square root of 2, because it's square root of 2 over 1. And the reciprocal of 1 over 1 is still 1. Okay? So we got that one filled in. "30-60-90s" come from, no, that doesn't look right. It still doesn't look right, but I'm going to go with it. What's that called?
Equilateral.
Equilateral. So if it's equilateral, meaning all sides are the same, what else do I know? All angles are the same. What do I know about the triangle sum? All interior angles of a triangle have to add up to 180. So if all angles are the same, I take that divided by and get 60 in each corner. Now what if I were to throw my Do you remember what that's called? Ooh, close. Altitude. The apophthegms are used in polygons. Say I have apothem is distance from the center to the side, perpendicular. So yes, it is. It's an altitude, but it also happens to be a perpendicular bisector of the base. Also happens to be an angle bisector of the peak. So this is 30 and 30. Well, if all of those sides are the same, I can put the same thing for all of them. I'm not going to use x just because I know what's coming and I know you don't like fractions. What if I called the whole side 2x? What are each of these now? You see how you wouldn't want to start with x and then call them x over 2? I know y'all don't like fractions. All right. Then, if I'm purely looking at a 30, 60, 90, can you get me that? Okay. I'm looking for a leg. Hypotenuse squared minus leg squared. Those are my ratios. 1, 2, square root of 3. Okay. So that's where these come from. It's not just we're taking numbers, pulling them out and saying, here you go, deal with them. Okay. These ratios and these numbers are grounded in mathematical fact. So you should have on here 1, 2, square root of 3. The way that you write ratios is from least to greatest. So 1, square root of 3, 2. Do you know ballpark what square root of 3 is? Grab a calculator. Should be like 1.729, I think. 7 what 2? 732. What's the 29? Square root of 7? Oh, whatever. Okay. So about 1.73-ish then. That's why 1, 1.73-ish, 2, they go in order from least to greatest. That's also how I remember what angles they go with. Because the smallest angle goes with the smallest side. The biggest side with the biggest angle, the middle angle with the middle side. Okay? So once I have that, we start filling stuff in. Oh. Okay, so y'all got this. 30, 60, 90, square root of 3, 1, 2. Let's start with 30. From the 30, opposite over hypotenuse. 1 over 2, 1/2. From the 30, adjacent over hypotenuse. From the 30, opposite over adjacent and rationalize.
Square root of 3 over 3.
Yes. Remember, if I got 1 over square root of 3, I need to rationalize it. Flip them all. Cosecant. Instead of 1 over 2, it's 2 over 1. Instead of square root of 3 over 2, it's 2 over square root of 3, and you need to rationalize it. 2 root of 3 over 3. Instead of square root of 3 over 3, now this is the funny part. If I flip that and rationalize, I get 3 root of 3 over 3, and then the 3's cancel. But it would have been faster if you had just said adjacent over opposite. Square root of 3 over 1. Okay? So each has their merits. That was from the 30. I'll flip it around. Now we're going to go from the 60. So remember, now this is opposite. This is adjacent. This is still the hypotenuse. From the 60, cosine, adjacent over hypotenuse.
Adjacent or opposite?
Opposite over hypotenuse. Okay. Word's bad today. What else?
1 over 2.
1 over 2. I want you to pause and look at sine and cosine for 60 and 30. What's 60 plus 30?
90.
What do you call angles that add up to 90? Complementary. Complements, sine and cosine. They go together like that for a reason. The sine of this angle is the cosine of its complement. You're going to start seeing a lot of these ratios repeat themselves or have reciprocals, and they're going to keep spitting things out in that pattern where this is going to swap as well. Sine swaps with cosine. Secant swaps with cosecant. Tangent swaps with cotangent. Okay? Which is really nice because effectively I don't have to think about any of these if I just know that this is the complement. If I just find one of them and I know its complement, then I can move u over here, reciprocals go there. Move u over here, reciprocals go here. Flop u, swap them. Okay? That's really handy where you only need to find 3 of the measurements. Y'all, this page, I'm not joking. Flashcard, Quizlet, Kahoot, something. You will be doing this a lot. When you move on to trig, Mr. Spear does not allow you to have the notes for the unit circle or these special right triangles because it's all these same numbers over and over. Like once you understand the unit circle, it's still taken down from last year. The unit circle. It looks like a lot of stuff. This is these 2 triangles. Over and over and over and over and over and over. Kit and calendar, kit and calendar, kit and calendar, kit and calendar. It is just these triangles on repeat. And it is the foundation of everything that we're going to do. Y'all got a calculator. We just said the sine of 30 was 1/2. Confirm this. The sine of 30 is 1/2. The collective, what? I want you to look at my screen and your screen. One of these things just doesn't belong here. Okay. Radians is a different measure of angle. And we will get to it. In fact, that's section 4.2. Okay. We will get to radians. You should have done it in geometry. Even in the before times, they didn't show kids that in geometry, and I kept telling them to, and they got mad at me for telling them to do it. Radians is a measure that we are not aware of yet. Make sure your calculator is in degrees, and if you need to make a note to yourself every time that you reset your calculator, every time you second plus 7 enter 2, every time you stab it in the back, it defaults to radians. Boy, it would suck to do a whole test in radian mode if it was actually supposed to be degrees. Hint, hint, my ACT kids this weekend. So, nice and simple, just go to mode.
Is the ACT in degree or radians?
Both. See, when we're in radians, we're going to write it in terms of fractions with pi. I don't say 0.6819 radians. I say something like negative pi over 6 radians. Okay, which is also why kids don't really like this chapter, because you have to write it in terms of pi. So, make sure you're in there. And now, double check it. Sine of 30 is 1/2. Now, we know that the cosine of 30 is square root of 3 over 2. I want you to do what is the cosine of 30 with a calculator, though. You're like, that's okay. I'll just have it, put it into that, fraction thing for me. Oh wait, it's not a fraction because a fraction is a rational number. And this has a radical in it, so it's not a rational number. But if you're rocking a scientific or a Casio, right? Those ones will do radicals. Am I?
I don't know how to change it.
Huh. Setup. Second setup. There you go. Yeah. If you get scientific calculators, these TI-36X Pros, I really like these. And almost every $10 Casio that you can get from Walmart, they'll write them in simplified radicals. The TI-84, the graphing calculator, will not. So just be aware of that. So if I said that the cosine of 30 was this, and I know that the square root of 3 over 2 is also that, that tells me that these values are stored in my calculator. If these values are all stored in my calculator, that means that all of the ratios are stored in my calculator. So if all of the ratios are stored in my calculator, I get to use it to solve for missing parts of a triangle. From the 42, what two things are we talking about? X and 18. What are those? Opposite, adjacent, or hypotenuse? So if that's adjacent and hypotenuse, which trig ratio is that? Cosine. So the cosine of 42 is supposed to be adjacent over hypotenuse. It's just a ratio. Solve it. Now, y'all remember Jesus fish? Multiply the two that line up, divide by the one that doesn't. It makes an alpha. Multiply the two that line up, divide by the one that doesn't. It's the same as I would multiply these two. 18 cosine of 42 is 1 times x divided by the 1, right? It's a shortcut. I do this with algebra half where they just make their little alpha on there, multiply the two that line up, divide by the one that doesn't. The reason I say that is because this is my answer. This is my actual factual expression answer, the correct way to write it. Now, again, I go into Necht Home Center and I tell them that I need 18 cosine of 42 feet of 2 by 8 to finish off a dog pen. They just blink at me awkwardly. Okay? So then give me the decimal approximation with it. I need to see this. The decimal approximation is going to be handy later when we're working in context of a problem. So I would just 18 cosine 42. Ba-dum, bump, bump. That's an irrational number. Okay, I can't write that as a fraction. So I just have to say 18 cosine of 42 approximately 13.377. We're always going to go 3 places. I don't care what the book says. In fact, doing trig values in geometry is where my 3 places rule came from. Because if we go to hundredth place value, things start getting wonky. I try to do something like find the surface area of the Great Pyramid of Giza, and because you went to the hundredths instead of the thousandths, now you're off by 500 square feet. Okay? But if I go to the thousandths, I just found by doing a lot of problems, if you go in the thousandths, you're still pretty flippin' accurate. Okay? So just go to the thousandths. I don't care what the book says. So,
Is there a ratio for every single kind of right triangle?
because it's calculated based on the ratio itself, like side to side. And those values are an algorithm. So I can put whatever I want in there. It could have been 18 cosine of 23.69856 over 35 pi. Yeah. It's still going to have it in there. Okay? So it's just a ratio of sides, and those ratios are programmed in as an algorithm, which allows you to solve for missing things. Go find missing things. Sometimes you got to use sine, sometimes cosine, sometimes tangent. Since they're not buttons on the calculator, you won't use cosecant, secant, and cotangent. Oh, good. No one got my joke. Ba-dum-bum. Dad jokes for days. Get it? Z cubed, Z's, sleep, that thing you don't get when you're a parent. Remember, write them as an expression. You might write it as 15 sine of 41. You might write it as 15 over sine of 41. Okay? You might write side length as 312 tangent of 48. It might be 312 over tangent of 48. Multiply the two that line up, divide by the one that doesn't. Okay, like that. You identify opposite adjacent hypotenuse. Which trig function am I working with? Set it up as a ratio. Cross multiply and divide. Leave it as an expression. Write the decimal equivalent if you choose. Actually, I'm going to say we should just write the decimal equivalent because we want to get in the habit of double checking our calculator for that whole radian degree thing. You don't want to just write everything in expressions and then it comes time for a quiz or a test or an ACT where it says how far is it from this flagpole to that flagpole, and you haven't been keeping that radian degree thing in mind. Okay. The other one, from here, I have opposite, I have adjacent, that's tangent. I'd say the tangent of 21 is opposite over adjacent, 9 over x. Multiply the two that line up, divide by the one that doesn't. It's the snack that smiles back. You get x is 9 over tangent of 21, which is about a thing. Okay? Yay? Okay, it's just faster if you do this multiply divide thing. If you want, you can say 9 times 1 is 9, x times tangent of 21 is x tangent of 21, and then you have to divide to get x by itself. But if you can one-shot it, then one-shot it. Okay? It's a whole room full of bad guys. Just throw the dynamite in the door and keep going. Okay? Just make sure it wasn't their armory, right, Matt? First D&D campaign we ever did, guy went flying 25 feet across the room. Only thing that stopped him from dying was the door. Can I just throw an explosive in there? All right. Were you knocked out for like 5-6 turns too? Oh yeah, he got wrecked. Then he fell in a pit or something too. God, you're just not very lucky. Anyway, blah blah blah. Do the exact same thing except now it's words, right? What do I have opposite, adjacent, hypotenuse, set up the ratio, cross multiply, divide, get your answer. I want you to do both, just because I know we need practice with that if we're a little bit shaky on our ratios. Okay, it's the exact same thing. There's just words with it now, so having that decimal equivalent really matters. If someone says, how far do you need to go to the finish line? Right?
So
Hmm.
is like this equivalent to cotangent? Or
No, don't, no. Because you're putting that on the value, not on the function.
well, it worked over here.
Oh, wait. Say it again. Cotangent?
Yeah, cotangent, because not
Yeah, because that puts 1 over whatever you just said. Okay. Yeah,
that one.
should be.
That one worked.
Yeah, it should be.
Yeah.
Where you got to be careful is how you write it. Because if it's like 9 times tangent of x to the negative first, that puts 9 over it. It doesn't put the entire thing on the denominator. So just be careful what you're trying to do. You might need parentheses to put the whole thing on denominator, if that happens. Opposite hypotenuse. Opposite adjacent. Don't. Notice I'm writing them as a 75 as a coefficient of tangent of 48. Okay. Just like when we were dealing with our radicals and all that kind of stuff, it looked kind of awkward if I said tangent of 48 times 75, because then you need parentheses to say it's only 48 and then times 75. Just like when we had our log problems. Yeah, I could write it as 2x log 3, but it looked kind of funky. I could write that as tangent of 48 by 75, but it looks kind of funky. So that's why we're writing it like this. Okay. Do I need to go through them, write them out? I saw a couple of us give the bunny snowball from Pets, Secret Life of Pets. Seen that GIF with him just twitching? Okay. I saw that expression among a few of you. Do we need to go through them? Like, speak up. Okay. Okay. Wee! Words! Yeah, you can do it when there's a triangle just sitting there in front of you. Can you make the triangle? The number one problem that kids come back to me for help with when they're in trig or physics is at the beginning of the class when they just don't know how to draw it. Can you draw this? When in doubt, draw it out. If you're not sure about your directions, remember, never eat soggy waffles. North, east, south, west. The north-south axis would be your y-axis. The west-east axis would be your x-axis. They are perpendicular. So when they say something is due east, it tells you it's perpendicular 90 degrees to north. I don't think we'll have time in this chapter, but all of this should be reviewed, and you should have done vectors in geometry, basic right triangle trig vectors as well. I don't think they've done that as long as I've been here. Finn, stop making things extra complicated.
It's the only way to entertain myself.
Could go back and do some missing assignments. On a college campus, the library is 80 yards due east of a dormitory. So, I'll call this D for dormitory. Dormitory words. Nah. Library is due east, so it's going to be over, due east. The college is constructing a sidewalk from the dormitory to the recreation center. Okay. The sidewalk will be at a 56-degree angle with the current sidewalk between the dormitory and the library. So I know I'm going to have 56 one of those places. Which is it? It says from the dorm to the rec center. So there has to be a 56-degree angle here to the rec center. And the rec center is due north of the library. Okay. So I've got a 56. I've got that. What else? 80 yards due east. To the nearest yard, how long will the new sidewalk be? Opposite adjacent hypotenuse. I've got an adjacent and a hypotenuse, which means I've got cosine. So the cosine of 56 is adjacent over hypotenuse. Multiply the two that line up, divide by the one that doesn't, getting x is 80 over cosine of 56, or about how long?
143.063.
Sounds right? I mean, it's right proportionally. 143 and change. Okay. So just be aware that some of the word problems might include your cardinal directions. Up at the top, inverse sine, inverse cosine, inverse tangent. It said that -1, when they put it on the name of the function itself, it means inverse. So far, what we've been doing is we would say like sine of 30 is 1/2. I was plugging in 30 to the sine function. I was getting out 1/2. I was plugging in an angle. I was getting out a ratio. Remember our inverses and swapping labels? So if regular sine is throw in an angle, get out the ratio, what is inverse sine? Put in the ratio, get out the angle. Okay? Inverse sine can also be called arc sine. Can also be called arc cosine. Can also be called arc tangent. And that's honestly how I remember them, is arc functions find angles. Okay. So if the regular function is plug in the angle, get out the ratio, now the arc functions is put in the ratio, get out the angle. So try it. Y'all got a calculator. Do arc sine of 1/2, and it should spit out 30. Okay? I should be able to go backwards now. Arc sine of 1/2. This is also why we want to use the perfect values. Because if I were to use the arc cosine of, and then my square root of 3 over 2, I simplified it like a freshman by calling it 1.73. That's not simplifying, that's just losing part of your answer. Ruh-roh. Oh wait, no, it's square root of 3 over 2. Sorry, I'm tired. Arc cosine of 1.73 is square root of 3 divided by 2. Okay. It doesn't quite give me 30 degrees because I didn't put in the actual value. But if I put in the actual value is square root of 3 over 2, then it'll give me perfection. Okay? This is why we need to be in simplified radicals, why we need to have the correct angles, the correct expressions, because that allows me to maintain this accuracy. Which is also why when you do all of this and lots of it in physics, and he rounds every step of the way, kids get heated if they've been in PreCalc before. I'll come back to this. So find the missing measure. Well, if all those ratios and angles are stored in my calculator, that means I can use them in reverse. From theta. Okay. I've got opposite and adjacent. So I'd say that the tangent of theta is opposite over adjacent, 26 over 11. Well, I don't want to know what the tangent is. I already have the tangent. I want to know the angle. So we arc tangent the tangent of 0 inverse functions when composed will cancel each other out, resulting in the identity. So I get the arctangent of. Okay, that's why this works. You don't have to write all this. You just write arctangent of. Okay, so you identify what function are they using, what ratios do I have. You use the arc function instead. Alakazam, you get yourself a angle. So what's that? It's twice as big, so like 65 something. What? Okay, 67 and change. So oh, beat you to the problems. Poor favor. What? So
Arc secant and
no, because secant and they're not on the calculator at all. But just like you had, you could find secant by doing 1 over cosine. You can find an arc secant by doing 1 over arc cosine.
are they used at all?
No. That's why they're not on there. Like, why would I use the reciprocal of the thing if I can just do the thing? It's something handy to know. You will use it later on in trig identities. But for the most part, those other three, they are the redneck cousins of the ones we actually want to deal with. Curious. Which one? They're both right, aren't they? Okay. I would take either one. I would take this one because it's simplified. I would take that one because it's the actual values from my problem. Either way, if you want to be real grumpy about it, yeah, you'd probably simplify. But I'll take the other one because, again, this is an expression value. You're going to give me the decimal equivalent anyway. Same thing over here. I've got adjacent, hypotenuse, arc cosine. Okay. Check with your neighbor, just make sure you're getting the same thing so I don't have to press a button. Hey. Almost there. I think I get to set them loose on. Oh no, what's that? Okay. Pause. So. Oh. All right. Oh wait. We're just like there. And fin. Okay. No, we're